Hi, everybody. Welcome back to Intro to Physics. This is lesson 21, so we are almost at the end, and we're going to pick up where we left off yesterday with gravitation. So let's go ahead and do it. The question that we ended with yesterday was how can we find the mass of the Earth? In those example problems that we've been doing yesterday, I had just given you the mass of the Earth, but of course, that wasn't a quantity that was always known. We had to figure that out at some point. But you can't exactly just like take a planet and put it on a scale and see how much it weighs. So we kind of have to go about finding the mass of the Earth in sort of a roundabout method. And the thing that we're going to do, well, the thing that we're going to use to do that is the moon, which does actually have a sort of roundabout method because it orbits. So its orbital period is about 27 days, 27.32 days. And that is very easy to observe, right? If you just watch the phases of the moon, because the moon's phases are caused by its motion around the Earth, and how much light is hitting the sun on the portion that is facing us. Um, so the orbital period is very easy to determine by just tracking the phases of the moon. They knew this for a long time, the moon's orbital period. To figure out its orbital velocity or its angular velocity, we just need to take, remember, its total distance that it travels in one orbit, so the circumference of a circle, more or less, divided by the amount of time that it takes to make that orbit. So 27.32 days is not a very metric friendly unit, right? We need to convert that to seconds, for example. So going way back to chapter 1, units and unit conversions, if you remember, we would set them up as fractions so that the units on the bottom would cancel out units on the top. And by setting up this series of ratios, we can get it to be the units that we want. So it covers more or less a circular orbit. This is an approximation. So 2 pi radians is a complete circle. So that's its distance, its angular distance. And the amount of time that it takes is now going to be in seconds. So that gives us an angular velocity of 2.66 times 10 to the negative 6 radians per second. The distance to the moon, based on its orbital period and velocity, we can figure that out to be 385,000 kilometers, again, approximately. And so using some of these equations that we went over yesterday for circular motion, right, we have this acceleration due to gravity, which is now a centripetal acceleration because gravity is what's pulling into the center. Centripetal means pulled in. So that centripetal acceleration, big G times the mass divided by the distance between the Earth and the moon squared. And remember that distance is from their centers, not from their surfaces. And then we set that equal to an equation for rotational acceleration, or angular acceleration, which is r omega squared. So we can figure out the mass of the Earth, I'm sorry, not the Earth, mass of the moon. So we have our distance, our orbital distance here. We have our angular velocity from up there. We have big G, which remember is a constant. That's always going to be the same value. And so we get a mass of 6.05 times 10 to the 24 kilograms. Sorry. So I'm sorry, I told you before this is the mass of the moon. I lied. It's the mass of the Earth. So sorry, my brain is right now. But anyway, this is our approximate mass of the Earth based on the moon's orbital parameters. Now, again, this number is slightly different than the one that we were using yesterday. We were using 5.97 times 10 to the 24 kilograms. But remember, this is assuming that the moon has a perfectly circular orbit, which it doesn't. Most orbits are not perfectly circular, right? Kepler discovered that the orbits of planets are elliptical, and that solved a lot of problems. So we get an approximate mass of the Earth to be about 6 times 10 to the 24 kilograms. Okay, so when we're thinking about gravity, yesterday we saw Newton's universal gravitation formula, right? Big G times mass 1 times mass 2 divided by r squared. So if the gravity outside of Earth or outside of the sun or outside of a planet looks like a 1 over r squared function, right? Proportional to 1 over r squared. What does the gravity inside Earth look like? So if we went to the exact middle of the Earth, like if we could drill down through the Earth, I guess when you're growing up, you always say like, oh, I'm digging a hole to China. Like that's on the other side of the world for us. Um, if you could dig down through the center of the Earth, would you feel extremely intense gravity due to that 1 over r squared relationship? So take a quick second, think through this, see if you can figure this out conceptually. So hopefully you have an answer in your head or a potential answer in your head for this. Either you would feel extremely intense gravity because the mass of the Earth is a constant and doesn't change, and your radius is going to 0. So now you have this like infinitely large force of gravity. Or the Earth's gravity is now pulling you out instead of in, so you would get ripped apart. Or the Earth's gravity cancels out in different directions and becomes 0 at the center of the Earth. That's actually the right one. I mean, that's the best case scenario, I think, too. Um, so here's a picture of what is happening here, right? So we have this kind of tunnel drilled down through the Earth. And in this case, we're dropping a ball through instead of like dropping yourself through. Can you even drop yourself? I don't know. But anyway, here's the Earth. And so as this ball is falling, we only count the mass of the Earth that's inside a sphere that's at the distance the ball is located, right? So that's called the enclosed mass. So you can imagine, as this ball is falling down farther and farther, that kind of darker orange circle is getting smaller and smaller because the mass that's enclosed within that kind of imaginary sphere is getting smaller and smaller. But there's still mass outside of that sphere, right? It's not like we're compressing the Earth to be that size. So there's mass inside this enclosed circle, there's mass outside of that imaginary sphere, and those two kind of cancel each other out. So the mass inside is pulling it inward, and then the mass kind of outside this circle is sort of pulling it outward. So what would happen here, if we could track the progress of this object, this ball, is that it would fall through the center, speeding up as it goes, and then as it's getting farther away from the center, it slows down until it's almost at the surface, right? Because you dropped it from rest. So ideally, it would be at rest again, somewhere near the surface. And it would kind of continue to just oscillate back and forth, losing some energy. But really, that energy is being transformed into other kinds of energy, heat, for example. So it would continue to oscillate back and forth until it kind of reaches a stopping point there at the center of the Earth. And so what we end up with is this sort of linear relationship with gravity inside the Earth, even though the gravity relationship outside the Earth is what we call an inverse square relationship, so proportional to 1 over r squared. So if we wanted to calculate like the idea of acceleration due to gravity inside the Earth, we would start the same way, right? G, or the acceleration due to gravity, equals big G times the mass times the distance between their centers. But now the mass that we're using is that enclosed mass within that imaginary sphere. And to figure that out, we would need the density of the Earth and the volume of that imaginary sphere, which is 4/3 pi r cubed for a sphere. Right, so that means the mass is the average density of the Earth times 4/3 pi r cubed. We can plug that into our equation for mass, and we can see that we have now r cubed on top over r squared on the bottom. Right, so when you have something that's the same on the top and the bottom of a fraction, you can simplify, cancel it out. So this r squared on the bottom cancels out an r squared on the top, and we're left with just an r in the top of the fraction. So that means our acceleration due to gravity inside the Earth is big G times 4/3 the density pi r. Right, so the mass of the Earth then um, is 4/3 times that density times pi r cubed, right? And so we can see here that we get this kind of like similar factor of 4/3 pi times rho. Okay, and here we have this ratio for the mass of the Earth proportional to that distance that we are away from the center, that enclosed distance. So if we were considering the whole Earth to be our enclosed distance, then we would get the entire mass of the Earth, right? But as that imaginary sphere gets smaller and smaller, right now we're enclosing less and less of the Earth's mass. So we can see then that the acceleration due to gravity inside of the Earth is proportional to just r, right? It's not proportional to r squared anymore because that factor has canceled out. And so if we were to set the surface as kind of our checkpoint, like does this math make sense? Then we're dealing with the entire mass of the Earth divided by the entire radius of the Earth squared. And that's the equation that we started out with, right? So that's good. That makes sense. That means our equation is, um, logical. So if we compare the acceleration due to gravity inside the Earth somewhere to the acceleration due to gravity at the surface, we see that it depends on where the radius of that imaginary sphere is located. Right, so this means that gravity increases as you get farther from the core. So let's imagine now that we're at the center of the Earth moving out. The gravity increases as you get farther from the core, proportional to r. But then once you hit the surface, you're no longer increasing the amount of mass that's contained within your imaginary sphere. And so at that point, we're getting farther and farther away from our mass, which is now, it's constant because it contains that whole Earth. So at that point, from the surface outward, it decreases proportional to 1 over r squared. When you're inside the Earth, since you're adding to the mass of that imaginary sphere, right, it's increasing as you get farther away from the core. Okay, so this is the graph of what this would look like, right? So here we are at the center of the Earth, and the farther out we move from the center, the more the gravity increases, right? Because we're increasing the mass inside our enclosed circle. Then once we hit the surface here at the radius of the Earth, then we see it drop off according to that 1 over r squared law that we talked about yesterday. Okay, so so far, we've been really just considering the gravitational attraction between two objects. So, like the Earth and the Sun, or a ball and the Earth, what have you. But since we're dealing with forces and forces are vectors, we can combine multiple forces together using vector mass, so vectorially. If each of these two masses exerts a force on a third mass, so now we're dealing with three objects instead of just two, then the total force on that third object is the vector sum of those forces. So this is called superposition of forces. And we've done things like this before with just our vector math back in chapter 1 and our Newton's laws, the forces, adding together multiple forces, how that affects things. Um, and really, this is more accurate to what real life is like, right? In space, you don't just have two objects, you have quite a few objects. And especially if we're dealing with like stars and star clusters, you have a lot of objects really close together that are definitely gravitationally interacting with each other. Um, we talk about, well, my dissertation research is on binary stars and how multiple stars interact with each other as they orbit around each other. So when we're dealing with these multiple star systems, this kind of vector addition, this superposition of forces, is really important to consider. So here's an example of a triple star system where we have three stars kind of orbiting around each other weirdly. So many of the stars that you see in the sky are actually systems of two or more stars that are held together by their mutual gravitational attraction. So when you look up at the sky, you actually can see, well, actually, a lot of the stars that you see are probably binary stars. They probably have something orbiting around them. So suppose there's a three-star system at an instant when the stars are at the vertices of a 45-degree right triangle. Okay, ideal case. Find the magnitude and direction of the total gravitational force exerted on the small star by the two large ones. Okay, so here we have a system of three stars kind of orbiting around their common center of mass. We have a small star, which is, just a measly 1 times 10 to the 30 kilograms. Oh, how cute. And then we have these two bigger stars, which are both about 8 times 10 to the 30 kilograms. So to give you a little bit of perspective, the sun's mass is about 1.99 times 10 to the 30 kilograms. So this star is a little bit smaller than the sun, and these are quite massive compared to the sun. And so we have their distances away from each other, about 2 times 10 to the 12 meters for the two large ones, and for the small and large one. And we need to find the total gravitational force on this small star because of these two large stars. So if we just examine this, kind of break it down into chunks, right? The force on the small star because of that upper large star, the orange star, we can use Newton's law of universal gravitation, big G mm over r squared. All right, so we plug in big G, which is our constant, the mass of the big star, the mass of the small star. Now the distance between these two stars, we can see this is a triangle. So this hypotenuse distance, we can use Pythagorean theorem to find, right? So this squared plus this squared equals this squared, which is convenient because we need that distance squared in our denominator anyway, right? So we'll just add together those two distances squared, which gives us r squared. And so that force that this small star feels because of the first star is 6.67 times 10 to the 25 newtons. Now, similarly, looking at the force that it feels from this other star, this red star, we set it up the same way. We have the same gravitational constant, mass of the big star, mass of the little star. Now the distance between those two stars is is just this 2 times 10 to the 12 meters. So we square that distance. And that has a gravitational attraction of 1.33 times 10 to the 26 newtons. So a larger force of gravity, which makes sense because it is a little bit closer. And the closer you get to something, the more gravitational attraction you feel from it. Okay, so we have the two components. Well, I guess the two forces, but that's not necessarily the vector sum of them. That's just the two forces individually. How do those forces work together? Right, so thinking about the components of these forces, right, this first force from this first star, if we're looking at just that x component, we're going to plug in that force times the cosine of the angle, 45 degrees. Right, it's a 45-degree right triangle. So that gives us an x component of the force of 4.72 times 10 to the 25 newtons. The y component of that force, remember we'll use the sine in this case because this is the side of the triangle that's opposite to our angle. So that's our force that we found times the sine of 45 degrees. 45 degrees is a great angle because that means we'll get the same result for x and y components. This second star, this red star, only has an x component to its force. Right, so that was the same value that we found before. It does not have a y component. So if we figure out the total force, its components, again, this is going back to chapter 1, vector addition, vector math. The x component of the total force is those two x components added together. So 1.81 times 10 to the 26 newtons. And the y component of that total force is the y components added together. So 4.72 times 10 to the 25 newtons. Okay, so we have the components of that total force. We do not have the magnitude yet. So let's find the magnitude. Remember, magnitude of these components is basically the Pythagorean theorem. Right, so we take that x component squared plus the y component squared, square root that answer, and that gives us a magnitude of the force of 1.87 times 10 to the 26 newtons. The direction of this force will use the inverse tangent of the y component over the x component, just like we did way back several weeks ago. Right, so we get an angle of 14.6 degrees. Right, so that's this dark vector F here, the resulting gravitational force from these two objects on this smaller star. Of course, in an actual cluster, you'd have way more than 3 objects all interacting with each other. So this math gets very complicated very quickly. Okay, so in this same scenario, let's find the acceleration of this small star. How would it move because of this force? Right, so there's our magnitude. We're assuming here, again, because this could get very complicated very quickly, so we're just going to assume that there's nothing else over here that is a significant source of gravitational attraction. Right, so the only gravity forces that this little star feels are because of these two big stars. So from Newton's second law, remember the net force equals the mass times the acceleration. So the acceleration is the net force over the mass. Our net force is that force vector that we just found. The mass of this small star is 1 times 10 to the 30 kilograms. So that's an acceleration of 1.8 times 10 to the negative 4 meters per second squared. Not a huge acceleration, but stars are very big. Okay. Any questions about this example before we move on? Okie dokie. So some interesting things can happen when you're dealing with multiple objects, um, all gravitationally interacting with each other. There are some points in that system. So, for example, like the sun, earth, and moon. There are some points in this system of objects where the gravitational force from the sun is balanced by the gravitational force from the earth or from the moon, or there are just some really interesting things that happen in real life because of these interactions. And so these special points where gravity does kind of weird things are called Lagrange points or L points. So these are the points near two large bodies, one well, in orbit, right? So imagine the sun and the earth, where a smaller object like a satellite, for example, will maintain its position relative to the large bodies. So this would be a stable or almost stable point where you could just kind of plop a satellite and leave it there, and it won't really need any fuel. You won't really have to do any like corrections to its orbit. Once you get it there, you can basically like turn off the navigation and it will just stay there um, at that same distance from these objects. It's very interesting. So at these special points, the gravitational forces of those bodies, the centripetal force of the orbital motion, um, and sometimes this Coriolis acceleration, which we might talk about tomorrow when we talk about rotational motion, they all match up in a way that create these stable points. So in this Earth Sun system that you can see in this picture here, here's the sun, here's the Earth. There are 5 points that are called these L points, these stable points. And they're all in the orbital plane, so they're like in the same plane as the Earth as it orbits around the sun. But they're well, they'd be different for different objects. So, for example, the Earth and the Moon would have slightly different Lagrange points. The Sun and Jupiter would also have Lagrange points, but they would be slightly different, given those orbital parameters. So here's the L1 point. It's between the Earth and the Sun, right? So I don't we're not going to go through like all of the math of this because this is sort of advanced. I don't think I learned about this until orbital mechanics. Maybe we talked about it in physics 1, but not in a whole lot of detail. Again, I just want to introduce this to you. So this L1 point is between the Earth and the Sun. So this would be basically where the gravitational forces from the Sun and the Earth would kind of balance out. And it would just be a satellite could just kind of chill there, right? So if mass 1 is much larger than mass 2, kind of like the sun and the earth, right, then this radius is big R cubed times the square root of mass 2 divided by 3 times mass 1. Right, so Lagrange point 2, L2 point, is beyond the Earth. And this would combine now not just gravity forces, but the orbital motion of the Earth as it goes around as well is important to consider. So actually, we do have some satellites here at this L2 point, and the James Webb Space Telescope, which was supposed to launch years ago, but it hasn't launched yet. But anyway, they're hoping to kind of just float that into the L2 point in the Earth Sun Moon system as well. Just kind of leave it there. This L4 and L5 points, we actually have what are called like Trojan satellites around several planets. So when we think about the other planets and their Lagrange points around their orbit too, a lot of the time they kind of push material around and pull material around, sort of like asteroids, these little satellites. So Jupiter, for example, at its L4 and L5 points, it has more than 1 million of these Trojan satellites, these like asteroid type objects that are just kind of like chilling around in the same orbit as Jupiter, just kind of taking advantage of um, the motion of Jupiter to push them around or pull them around. It's kind of interesting. Anyway, the math for those other locations are more complicated than those equations that I have for L1 and L2. So I'm not going to go into those. But yeah, I just thought those points were kind of interesting to mention. So if you study aerospace or astrophysics or something along those lines, then you'll see this again later on. Okay, so gravitational potential energy, we have to revisit this too because we talked about this the other week in our energy unit. So previously, gravitational potential energy, or UG, was just equal to mgh, right? The mass of the object times the acceleration due to gravity times the height of the object above your reference point. Okay, so that's great if you're near the surface of the planet and g is constant. But since we're dealing with things outside of the Earth's surface, now we're not near the surface anymore, and g is not constant. So our equation looks a little bit different, just like our gravity equation looks a little bit different. So now our gravitational potential energy is negative gmm over r. Remember, the force of gravity is gmm over r squared. So this one is a little bit different. That subtle difference is important. Okay. So notice that there is a negative sign for this equation, and there is not a squared in the denominator. So this means that changes in this potential energy are more important than the potential energy itself. Okay. It's that change that really matters for us. So here's our equation for potential energy, gravitational potential energy. So at what point is this gravitational potential energy equal to 0? It would be at the center of an object, the surface of an object, or at infinity. Well, it's at infinity. It would be 0. Okay. So if we look at our equation, right, in order to make this equal to 0, the denominator here has to be a huge number, has to be infinity. And of course, we can't actually get to infinity, so this idea of a 0 gravitational potential energy doesn't really exist anymore for us, right? As you get closer to an object, so coming in towards Earth from infinitely far away, does your gravitational potential energy increase or decrease? Okay, so our gravitational potential energy would decrease because there is that negative sign in our equation now. So it gets more and more negative as your distance from the object decreases. All right, so let's take a look at one of these examples here. If we ignore orbital effects, a ball is dropped from the International Space Station 405 kilometers over the surface of the Earth. How fast is it going when it hits the ground? Okay, so we're going to try this 2 different ways, one using the old method and one using our new method here. I'm sorry, this equation should have a negative in there. Negative is important. Okay. So the radius of the Earth, 6,371 kilometers. The mass of the Earth, 5.97 times 10 to the 24 kilograms. Okay. So here's like a little sketch of what's happening. There's an astronaut up here in the International Space Station, which is hovering above one point on the Earth. They drop a ball from this height of 405 kilometers. So thinking about the old method that we had done, the change in the energy, conservation of energy, tells us that the change in the energy is zero. So its initial energy equals its final energy. So initially, this ball would have all potential energy, gravitational potential energy, and right before it hits the ground, it would have all kinetic energy, right, due to its motion. So it's mass times g times height, and I'm using 2 because we're talking about the mass of the ball, not the mass of the Earth, equals 1/2 times the mass of the ball times its final velocity squared. So once we plug all of those numbers in, do our math, algebra magic, we get a final velocity of 2,817 meters per second. Okay, that's according to our old method, our conservation of energy. Keep that number in mind. So our new way, again, thinking about conservation of energy, because that's always true, right? Energy is always conserved. So its initial energy is still equal to its final energy. Now its initial energy is gravitational potential energy, but at the end now, it still has gravitational potential energy because we're not thinking about it in terms of, the surface being our 0 point. The center of the Earth might be our 0 point here. Okay, so our potential energy initially is G m1, Earth, m2, the ball, divided by the radius to the International Space Station. Okay. The kinetic energy equation is the same as it was before, since we're just looking at the ball moving. And then again, we have this minus sign from our potential energy, G, mass of Earth, mass of the ball, divided by the radius of the Earth squared. Because even though it lands on the surface, right, remember the surface is no longer our 0 point. The center of the Earth is our 0 point. Okay, so this radius to the International Space Station is the radius of the Earth plus the height of the International Space Station above the surface. And then we're multiplying by 1,000 because we need that in meters as opposed to kilometers. So doing our same, kind of plugging in our numbers, doing our algebra magic, we get a final velocity of 2,733 meters per second. So, sorry, wrong way. So 2,733 compared to 2,817. You can see they're kind of approximately the same, but they're not identical anymore, right? Because we're not considering the surface to be our 0 point, and that makes a big difference in this new method. Okay. Example 5, from Earth to the Moon. So in Jules Verne's 1865 story, 3 men were sent to the moon in a shell fired from a giant cannon sunk in the earth in Florida. Now, I've never seen that giant cannon. Maybe I need to look harder. Neglect air resistance, Earth's rotation, and the gravitational pull of the moon. Wow, this is a very idealized problem. Okay, so find the muzzle speed needed to shoot the shell straight up to a height above the Earth equal to the moon's radius. So if we just fired it straight up to the moon, how fast would we need to launch them? And then find the escape speed, which is the speed that we would need to launch them to allow this shell to escape from the Earth completely. So not be kind of sucked into orbit around the Earth. It can just leave the Earth's orbit completely. Okay, so here's our picture. Right, here's the Earth with its mass. R1 is the radius of the Earth. R2 is to 2 times the radius of the Earth, right? So 0.1, 0.2. So once this shell leaves the cannon, only gravity is doing work, right? We're ignoring air resistance, which means we're ignoring friction. And we're ignoring the Earth's rotation and the gravitational pull of the moon. So only gravity from the Earth really is doing any work here, and energy is conserved, right? So our initial energy equals our final energy. So kinetic plus potential initially equals kinetic plus potential at the end. Now, remember that the shell will be momentarily stopped at that final location, right? Because we're trying to land it on the moon. So we're not going to deal with any final kinetic energy. We cannot assume that the initial gravitational potential energy is zero anymore, right? Because we saw in that last example that, even though the old way is a good approximation, it's off by 3% from the real way or this new method. Um, it's not good enough if we're trying to land people on the moon. Well, and in one piece. So we have our initial kinetic energy and our initial potential energy, which is equal to our final potential energy. Right, so as we take this equation, we're looking for that initial speed. And we can see we have this small m, the mass of the shell, plus the people, in each of the terms. So we can ignore that mass. It's not really important to know that. We know g, it's a constant. Mass of the Earth, we know. Radius of the Earth, we know. Right, so we can just plug in all of those numbers once we've gotten our equation. And we get a speed of 7,900 meters per second. That's fast. That's why we have rockets. I mean, that's 17,700 miles per hour. Okay, so second part of this question, find the escape speed. So the speed that would allow them to completely escape from the Earth's orbit. Remember, they can't completely escape from the Earth's gravitational attraction unless they're at an infinite distance away. But they can be far enough away that they will not be sucked into orbit around the Earth. So that's what we're looking for. All right, so this is really what we're looking for. Okay, this new distance, we have it at infinity, right? If we're trying to completely escape the Earth's gravity, it would have to be infinity. So if the shell barely reaches this point, right, because we want it to kind of slow down and stop at this infinite point, we still have conservation of energy, right? So we still have initial kinetic energy plus initial gravitational potential energy equals final kinetic plus final potential. Okay. At infinity, potential energy is zero. And since we're just barely reaching this point, we're going to imagine that it's coming to a stop at this infinite distance. It has no kinetic energy at that point anymore either. Right? So this speed that it needs, this escape speed that it would need initially, that's what we're looking for. Okay. So when we rearrange our equation to solve for escape speed, we get this equation right here, which is actually a very significant equation. This is one that I would definitely recommend that you write down on an equation sheet. The square root of 2 times g times the mass of the Earth divided by the radius of the Earth. Okay, this is our escape speed equation. And that works out to be 11,200 meters per second, which is 25,000 miles per hour. Right? That's why it's so incredibly difficult to get things off of Earth and try to like send satellites to other planets. For example, like the Voyager probe, which has exited the solar system. These probes that have gone to Jupiter and to Saturn and we have to launch them incredibly fast to get them to escape from the Earth. It's ridiculous. Okay, so there's our important equation to remember from this example. All right, so again, thinking to satellites, a circular orbit is always the simplest case. If we're trying to put something into orbit, not escape from an orbit, but if we're trying to put something into orbit, a circular orbit is always going to be the simplest to think about. Right? This means that the only force that's acting on it is gravity, which is directed in towards the center of the orbit. And so we're dealing with a centripetal force. And since we have a circular orbit, that means the satellite is in uniform circular motion. So at no point in its orbit would it be moving faster or slower than another point. It's moving at a constant speed in a nice circular manner. So we can use what we know about Newton's laws, right? Newton's second law and Newton's fourth law, this universal gravitation law. Right, so if our net force is mass times acceleration, and gravity is gmm over r squared, then gravity, gmm over r squared, is our centripetal force, which is calculated as mv squared over r. That means that our circular orbital speed, or the speed that we would need for a circular orbit, is the square root of gm over r, right? And this m is the mass of the Earth. Okay, this is an important equation to remember too. If we're trying to get something into a circular orbit around the Earth, we need to know the mass of the Earth and the radius that we want it to be, and that will tell us how fast it needs to be traveling in that orbit. Not how fast it needs to be traveling off the ground, but how fast it will be moving once it's in that orbit. Right, so that definitely depends on the radius of the orbit. The closer it is versus the farther away it is, that will make a difference on your speed that it will have. So many satellites have nearly circular orbits, again, because that's the simplest case to try to plan for. And actually, planetary orbits are also very close to being circular. So we'll talk about that in tomorrow. We probably won't have time to go through all of Kepler's laws today, but yeah, planetary orbits are very close to circular, except for Pluto, which is one of the reasons why it was demoted from being a planet. But anyway, for any particular radius, there is a speed, a particular speed that it will need to move at to maintain a circular orbit. And if it doesn't maintain that speed, then it will either spiral in towards the Earth and crash. And if it moves too slow to maintain that orbit, it will spiral in. If it's moving too fast, it will spiral out. So we need that particular speed for a given radius. But you'll notice that it does not depend on the mass of the satellite, just the mass of the Earth. Okay. So this equation that's in the box for a circular orbit is actually very similar to this equation for escape velocity. Look, there's a 2 up here. So the square root of 2gme over re, as opposed to gme over r, right? Very similar idea. So there's this quote that Robert Heinlein says, once you're in orbit, you're halfway to anywhere. Once you've established an orbit, you are halfway to your escape speed. Okay, you're halfway to anywhere you want. So if we want to know how long it will take to make a circular orbit, one orbit around the Earth, that's its orbital period. Remember, period is a capital T because it's an amount of time. And that's the circumference of the circle divided by the speed that it's moving at. Right, so the circumference of the circle is 2 pi r. R is the radius of from the center of the Earth to the orbit. So our velocity we know is square root of gme over r. Since that's in the denominator here, we flip the fraction to get the square root of r over gme. Okay, so now we have an r here and an r inside the square root. We can combine those. We just get a fractional exponent. So 2 pi r to the 3 halves, right? Because this is the 2 halves plus 1 half is 3 halves, divided by the square root of gme. And that is the period for a circular orbit. Okay, another important equation to remember. All right, so tomorrow we'll start here, going back to Kepler, summarizing very quickly his 3 laws of planetary motion and how they relate to circular motion. And then we'll talk a little bit more about rotational dynamics to kind of finish out the class. But if you guys have any questions, of course, you're welcome to stick around and ask. And if not, I hope you guys have a great rest of your day, and I will see you all tomorrow. Bye.